the question I want to ask you right now. You see some kind of wave traveling from the first medium into the second medium, and what could be happening? And these are possible answers, and this is how much time you have to enter your answer. All right, so, well, your answers almost evenly divided. Well, first of all, these are the variables we have to relate, and we know speed equals frequency times wavelength, and we can write this expression twice for each medium. The wavelength clearly changes. Actually, it shrinks. However, if we want to compare something, most important part is stating what doesn't change. And well, supposedly the speed of the wave is different in different media. We know for sure, for example, in water, sound waves travel how? Faster or slower than in the air? Faster, about 4 times faster. So speed also is different in different media. Frequency, what about frequency? Well, frequency is a property of a source. There is a source. For example, a speaker which pumping pushes on molecules, like say 100 times per second. Those molecules push on molecules in the neighborhood 100 times per second, and etc., etc. So the frequency is supposed to be the same along the way in any medium, because again, it's related to the source. Well, it could be a light source, same idea. So the frequency stays the same. And in this situation, we can say that speed divided by the wavelength is supposed to be the constant. So if wavelength shrinks, what does it tell us about the speed? V2, the speed in the second medium of this wave, is it greater than, equal to, or less than the speed of this wave in the first medium? That's my next question. So 1 for greater, 2 for equal, 3 for less. Again, almost even. speaking about speed number 2. That's how we could relate it to the speed number 1. So this ratio, if it's greater than 1, that means the speed in the second medium is larger than speed in the first medium. If this ratio equals to 1, speeds are equal. And if this ratio is less than 1, so that means the speed of this wave in the second medium is less than speed in the first medium. So in our situation, this ratio is what? Greater than 1? Equal to 1?
Less than 1.
Less than 1, yeah. Thank you for saying microseconds. That means this speed is less than speed in the first medium. Now we just said in water, speed of the sound is actually about 1400 instead of 300. So that cannot do air and water. It can't. So this doesn't work. If this doesn't work, that can't be right. So that's is the case. And you know from the movie that when light is traveling in one medium into another medium, it slows down. Well, in vacuum, there is no medium where light doesn't interact with anything. However, a light wave is an electromagnetic wave. It has two components, electric component and magnetic component. And any medium has atoms. Atoms have charges, protons and electrons. So electromagnetic wave starts interacting with those electrons. Interaction slows it down. That's it. So, like here in this picture, well, these dots represent wave fronts. Wave fronts of light wave. And because in a second medium, the speed of the light is slower, that means the wavelength also shrinks. But in addition to that, we can see that if light approaches the boundary between medium at some angle, light bends. And if I look at the, well, this works for any wave, sound wave, light waves. The difference is that light slows down in the medium, and sound waves usually speed up in a denser medium. And here we can see wave front changes. And because the wave front changes, instead of using wave fronts, we can use actually rays. Ray is perpendicular to the wave front. Not this one. Here, I'll try it. So instead of using wave fronts traveling over the boundary and bending, we could use rays which are perpendicular to wave fronts. And this picture shows clearly that when light encounters a boundary between two media, it bends. How? Well, you know the law. Yeah. If you introduce the angle of incidence and the angle of refraction, and you must remember, we measure those angles always towards the normal. This is the normal to the boundary. This angle is not that angle which is a part of a Snell's law, right? So if you're writing Snell's law, you have to introduce two indices of refraction. And in that case, you can write index of refraction of the first medium times the sine of the first angle has to be equal to the product of index of refraction of the second medium times the sine of the second angle refraction. That's what we call a Snell's law. And basically, this law describes all possible situations, all possible problems related to this phenomenon, refraction. Well, this is a reflected ray. Of course, when light encounters a boundary, getting partially reflected, partially refracted, and we know the angle of reflection is supposed to be equal to the angle of incidence. So that's the complete picture for the light traveling through the boundary. Now, this law involves two media. One we call the first one, another we call the second one. So, what is the medium number one? How can you describe what the difference between the first and the second? What do you think? Now it's not related to density or indices of refraction of particles. It's related to how light is traveling. If you have a boundary, then you have a light traveling through. That means there's always one medium in which light is approaching the boundary, the interface, and there is a medium in which light traveling away from the interface, right? Like in this situation, approaching interface, traveling away. The medium number one always is the medium in which light getting closer to the interface, and the medium number two is always the medium in which light getting farther away from the interface. That's why we call it 1 and 2. It's not necessary that this index of refraction always is lower than this index of refraction. No. Well, depending on the angle of incidence, the angle of refraction also changes accordingly to this Snell's law. We also can see what is happening if we change the medium when the index of refraction is not very different from the first one, the bending happening less. And at some point, as you know, the light doesn't bend at all. It happens when both mediums have exactly the same index of refraction. Well, let's take a look at actual light, actual rays. Let's see if I can use my camera today. So here, first, what I want to do, I want to take this laser pointer and I want to aim it like this. So this beam would travel through the center of this, well, semicircle. So light can be traveling through two boundaries here. First one, second one. And of course we have two questions. First question, what's going to happen here? So, oops. That's my first situation. The center was here. And light travels like that. So, I'm going to ask you a question, and your possible answers are: number one, it bends away from this dashed line. It doesn't bend at all. That's choice number two. And it bends away down. 1, 2, 3. think it's bent. Well, it's not. First, we just said there is one situation when light doesn't bend, when both media have exactly the same index of refraction. The second situation is, well, if you write the law, when this angle equals 0. In that case, sine of 0 is 0, the whole product is 0. That means this angle is also supposed to be 0, so there is no change, means doesn't bend. And in our example, if this, well, it's a semicircle, at the center of the circle, any line which is going away is basically a radius of a circle, and it's perpendicular to the line tangential to this circle. So if you have a ray traveling like this, it's traveling along the normal to the surface. So if you measure the angle between the beam and the normal, there is no angle, it's 0. That means the angle of refraction has to be 0 again. So it should go like this, and it should reach the center. That's the second situation when there is no bending. Well, let's see if I can actually aim it. Yeah, you see? Straight line, no bending. Well, here, the situation depends on the actual angle of incidence. Here, on this boundary, we analyze so-called air-water situation. Air-water situation is a name for a case where light is traveling from medium with low index of refraction into medium with high index of refraction. Air has index of refraction very close to 1, and plastic, glass, water, they all have index of refraction of 1.3, 1.4, 1.5, so low, high. Here on this boundary, on this interface, situation we call water-air situation. Here, light is traveling from medium with high index of refraction, 1.5, into the medium with low index of refraction, 1. And the result might depend on, well, how light is approaching that interface. Here, I'm not sure if you can see it. So here, the beam is just traveling straight through. Now, you can see it bends, it bends, it bends, and at some point it disappears here. There's no light anymore behind this surface, but where can you see it? You can see it inside. So now, instead of being refracted, light is getting reflected. How do we call this phenomenon? Well, someone's supposed to know. Anyone? Venture a guess. How would you call this phenomenon? If you say something, we'll call it like that from now on. Your name is going to be in the book, in the old books. Well, that phenomenon has a name, a total internal reflection, because it's happening inside the medium, it's reflection, and light getting completely, totally reflected back. That's why we call it total internal reflection. Well, before we go to mathematical description of total internal reflection, let's answer a couple of more regular questions. This one. Here you have 3 examples well, 3 pictures, I would say. And my question is, can all of these pictures actually be experimentally achieved? If I had a laser pointer and 2 media, could this happen? Could that happen? Or could that happen? And these are your answers. If you think only this case could happen, you can press 1. If you think only this case can happen, you can press 2. Only that, press 3. If you think that these 2 could happen, but that can't, you can press 4, etc., etc., etc. All right. Well, 1, 4, and 5 are most popular. Let's see. First of all, you have a page with a picture like that, and on that page, it's much easier if you actually could rotate and draw a normal to each situation. So here, if you want to apply a Snell's law, you need a normal perpendicular to the interface. Here, perpendicular to the interface should look like that. Here, it should look like this. Now, if you look at these pictures, there is one case which never can happen. Which is that? Never, under any circumstances. If you just see it, which one? 1, 2, 3, 2. Never can happen. Because in any situation, this is a normal, that's a fictional line, it's not a mirror. So your incident ray and your refracted ray is supposed to belong to different halves, to different sides of this plate. So wrong, completely wrong. Now, we have to look at the actual numbers. Here, light is traveling from medium with low index into high, low, high. And here, the same situation, low into high, 1.5, 1.6. However, in this situation, you see, well, relative to this line, ray bends towards the normal, getting closer. In this situation, if you look at this, light ray bends away from the normal. Of course, only one situation can be correct. Because if you have the same relationship between indices of refraction, you should observe the same bending. Which is correct for a situation low, high, I would call it, like a nickname, air, water. Light, how does it bend? Closer to the normal or away from the normal? Anyone? You've been so helpful. Closer or away? All right, I'm gonna give you another thing. So, if you apply the Snell's law, if you actually want to calculate that angle of refraction, that's what you're supposed to do. You have to calculate this combination of variables, right? That's what the Snell's law tells us to do. Now, again, the result depends on this ratio. That's the angle of incidence. This ratio, in general, could be larger than 1, equal to 1, and less than 1. So, if this ratio is equal to 1, both media have the same index of refraction. That means the angle of refraction equals the angle of incidence. That's it. If this ratio is less than 1, so 1, this is the medium number 1. This is the medium number 2. How do I know? Because by a definition, light getting closer to the interface inside in the medium number 1. So N1 equals 1.4 and 2 equals 1.6. Again, we call it air-water situation. Close, yeah. So, and in this situation, this ratio is less than 1. What does it tell us about this angle? If you multiply it by a number less than 1, your result is less than the previous number. So you should get a smaller angle. Smaller angle between what and what? Smaller angle between the refracted ray and the perpendicular. So this angle is supposed to be smaller than this angle, which means light bends toward the normal. And we're supposed to observe the same kind of bending in this situation. That is the correct picture, because it's the same case, air-water situation. However, well, the picture shows completely opposite, so this cannot work too. So two pictures are wrong, only one case could happen. Any questions? Well, let's see what other questions we have. Well, pretty quickly. Again, we just need to figure out the relationship between the angles. This is the normal. The angle of incidence, the angle of refraction. Now, if you look at the picture, the angle of refraction is greater than the angle of incidence. Angle of incidence is smaller. So this ray getting bent away from the normal. What case is it? Air-water or water-air? So a minute ago we said in air-water situation, light should bend toward the normal. This is a different case. Light getting bent away from the normal, so it's kind of water-air situation. Again, don't take it literally, it's just a nickname. But it means this index of refraction, which is number 1, because here light is approaching the interface, is greater than this index of refraction, which is number 2, for this boundary. Which means prism has a lower index of refraction. Here, a different case is happening. So now, if you're considering this boundary, which object represents medium number 1, and which object represents medium number 2? Light is approaching the boundary inside this prism. So now, if you want to write the Snell's law for this particular point, this has to be the medium number 1. This has to be the medium number 2. And if you look, you should have a picture. If you look closely, this angle is slightly smaller than this. Light bends toward the normal, as it's supposed to, when it goes from, well, air water, yeah, from medium with low index into medium with high index of refraction. Well, we answered, yeah, no bending, same index. Now, please take a minute and think about it. Again, you saw this in the movie, I think. I just want to prepare this particular experiment to prove you it's not fictional. I just named it. State. Okay. Well, that's right. All right, so we can see it being before, in, and after the brick. And if you look at this ray, and if you look at that ray, what can you say about those two rays? They're parallel to each other. Plus, that ray, second one, is just shifted a little bit up relative to the first one. How can we explain this mathematically? Again, we have to apply, of course, the Snell's law. Very simple. Which was it? This one. So, air, well, brick, here we call it water. How does it bend? Light is supposed to bend toward the normal. What is happening here? It's supposed to bend now away from the normal. So that's the angle of refraction. This is the normal, which is parallel to this normal. So this angle, let's call it number 2, is supposed to be equal to the angle of refraction. And this is the angle number 3. So the air has index of refraction equals 1. So 1 times the sine of first angle has to be equal to index of refraction of the prism times the sine of the angle of refraction into the prism. This one. This is the equation for the first point. For the second point, we should write n times the sine of second angle, because here, this is the angle of incidence. Prism now represents the first medium. Has to be equal to 1 times the sine of the angle number 3. Because now the air is the second medium. But this product equals this product, because these two angles are equal to each other. So this sine equals this sine, which means this angle equals that angle, which means those two rays have to be parallel to each other. But light doesn't leave this plastic brick here, it leaves it higher here. So this kind of brick just shifts their beam, but doesn't change its direction. So these are two standard situations. First situation, when light is traveling into water, and second situation, when light is traveling from the water into the air. I actually have I'm not sure if camera would help, but let's try. I actually have nice. So let's add some further. You see? This is the normal. When light travels from air into water, it bends closer to the normal. What is happening when light traveling from water into the air? Well, if you look closely, if you sit closer, you can see this beam is above the surface, but it bends away. And if I change the angle at some point, again, what's happening is there is no light above the surface. It's actually, where is it? It's hard to see. Getting reflected back. Well, at least one person should see it. It's getting reflected back. Well, we know the name. We call it total internal reflection. Most important fact is that for some angles, light actually getting out. But if we increase this angle, there are angles when light actually getting completely reflected. So between these angles, when light getting out, on those angles, when light getting reflected, it has to be some critical angle when it starts happening, when the total internal reflection starts happening. So how can we calculate that critical angle? Well, we just have to apply the Snell's law. Let's say N1, N2, and I want to call it water-air situation. So water, air, which means N1 is greater than N2. This is the normal to the surface. And I know for some angles, light is getting through. For the critical angle, when its reflection starts happening, light is neither getting through nor getting reflected yet. So it's basically kind of traveling along the surface. So this is the angle of refraction for the critical angle of incidence. That's the critical angle. That's the angle of refraction. What is the value of this angle? We have to measure it from the normal to the beam. What number? This is the normal. This is the beam. This angle equals what? Yes, U. 90. It's 90 degrees. By definition, normal is perpendicular to the surface, and beam is parallel to the surface, so it has to be 90 degrees. So now we can write the Snell's law very simply. N1 times sine of the critical angle has to be equal to N2 times the sine of 90. What is the value for the sine of 90? 1. So to calculate the critical angle, well, it's easier to calculate this sine first. We have to calculate this ratio. That's it. That's the critical angle. Well, the reason for total internal reflection happening is that the sine is a limited function. It doesn't have value greater than 1. So as long as this maximum value is reached, that's it. No more angles of refractions left. So when we aim the light at the angle larger than critical, it must reflect. Snell's law doesn't work anymore. Well, here, you look and you think about it, and I want to show you a couple of more examples of application of total internal reflection. Here, how do I want it? Okay. Just like that. It's not exactly the same prism, but it is a prism, and a lot of questions are related to prisms. And again, if we need to figure out what's happening to a ray traveling through the prism, we have to consider always two situations. And, well, if you look inside, you can see the beam is actually getting reflected here. It's traveling in, and try green, a little bit brighter, but there is no light coming out. It's getting reflected back. This principle actually is used in many optical devices, binoculars, for example. Instead of using a mirror, we can use just a transparent surface. However, for a situation with total internal reflection, it works like a mirror. And we can change the direction of the light with this prism. One of the most important applications of total internal reflection now is that, well, fibers. Any fiber optical device is basically a really, really thin wire like this. But light, if you light doesn't go out. It's traveling inside. You can actually see it. If it's close enough, how it's traveling inside and it's getting out at this end. So we can use this light guide to, well, transmit signals much more efficiently than using regular copper wires, for example. All right, here, the last question. What will happen? Well, again, we only have three cases. Number one, it just travels through without any bending. Number two, it eventually bends up. Or number three, it eventually bends down. So what do you think about it? The most important word here, okay, your answer, is it's supposed to bend. But how, the question is. And if you read the question, yeah, you see this word less. So the prism have index of refraction lower than the medium have. And medium, so this. So here, the first normal, so medium has a higher index of refraction, prism has a lower. High, low, water, air. Light should bend out away from the normal. So without bending, it would go like that, but it should bend away from the normal. And here, well, even if it bends slightly back, still, effectively, it bends up. And of course, if you had a different situation, if your prism would have index of refraction higher, like than the medium, like glass and air, in that case, light would effectively bend down.